This is lesson 7, and we're going to read through this material together. We're going to be talking about lines, angles, and planes. So if we scroll down a bit, the new concept has a lot of vocabulary words, and so we want to really be mindful about them. And I'm going to give you kind of a light conceptual understanding of what some of this is. So one of the words that's really a great word is plane. And the concept of plane is thinking, you can think about like a flat table or a flat TV screen or something like that that extends forever and ever in all directions. So sometimes in geometry, when we think of the word plane or when we think about a plane, let me use this symbol instead. When we think about a plane, we're going to think about flat space that extends forever and ever. And we'll use a figure like this to refer to a plane. So that's what a plane would be. A line, I'm sure you've heard of a line before and you know what a line is. But in geometry, when we talk about a line, we're talking about something that is extending forever and ever in two directions. It has no length because the length is infinite, and it's a collection of points all along the way. So I guess the idea of points should be discussed. And you know what a point is? A point is a place, it's a location. So I can literally have a point on a line, and I could refer to that point. When we have a point on a line, we refer to that point with a letter, say point A, as you can see down here. So a line has infinitely many points. Sometimes we can refer to 2 points on the line, and we can call that line line AB. So you could write the word line AB to refer to the line because of those 2 points, or you could write AB with a line on top. But notice how important it is to put those arrows on either side. So that's the 3 vocabulary words here. We're going to look at some other ones. So we have this concept here of array. An array, here it is, it's kind of like half of a line. It's like an arrow. So if you have a line starting from one point, so not a whole line, you're starting at one point, or you have what we call an endpoint, and then we go into one other direction forever and ever. That's what the arrow means. If we have that, that is considered array. That's considered array. And so what we would do is we'd call it ray AB. So that's ray AB. Sometimes we can write ray AB like this, AB with a little arrow on top of it. Please note that if you write BA with an arrow on top of it, you're not talking about this picture here. You're actually talking about this picture here. This orange thing that I'm drawing. BA has its start point at this endpoint B, and it goes in the other direction of A. But AB is the black one that I had there. Does that make sense? Hopefully it does. So you have to be careful when you are naming your rays, okay? So this ray is only called ray AB, written that way or that way. So we've got rays. We also have segments. And segments basically are a part of a line. So if I had a segment, say segment AB, keep using the letters AB. We can use any letter, by the way. If I have a segment AB, it has a start point and an end point. Let's just review really quickly. A line has no end points. It has infinitely many points on them, and we can talk about a line given 2 points. So we can say the line, we call this line AB. We use this symbol when we use line AB. Array has order. It has an endpoint, and then it goes off into one direction forever and ever. It starts at its endpoint, which sounds crazy, but that's where we will think about it starting at its endpoint, and we must name it the endpoint first and then the direction that it's going. So we name this ray AB. And here is segment AB, which has 2 endpoints, and we can actually call this segment AB or segment BA. The order doesn't matter at this point. And the way we would label that, the way we would write segment AB is AB with a line at the top or BA with a line at the top. Or of course, the words segment AB. So that's a lot of vocabulary words today. Let's go ahead and look at our first example. So here in example 1, we are asked to use symbols to name a line, two rays, and a segment in the figure. So let's take a look. The line clearly we could name like this, call it AB, and we can do that. Or we can call it BA. Lines, the way you name a line is interchangeable in terms of the order of the letters once you make sure that you have it in with the line with the arrows at the top on both ends. So this is how you would name the line. If you wanted to name two rays, so the two rays we could name would be ray AB or ray BA, and they refer to two different rays. We could name the segments. They asked us to name a line, two rays, and a segment. So a segment, we could name the segment AB like that, or that same segment could be called BA, and this would be the segment, the way of naming the segment. So that's all we were doing there, just making sure we understood the vocabulary and how that worked out. And so you can see that's what the answer would show there. Let's scooch up a little bit. So here in example 2, in the figure below, AB is 3, and AC is 7, and find BC. And I know we've worked on this before, and I know you know this, that this answer would be 4, and you're going to do that by subtraction. And that makes perfect sense. And that's exactly what the textbook tells us, because we know that segment AB plus segment BC is equal to segment AC. Moving on, we've got some more vocabulary words that we need to keep in mind. So one vocabulary word is intersect. To intersect is to connect at a particular point. These two lines intersect at M. So to intersect means to cross or to connect at a point. So they intersect there. Another word that is going to be, you're going to see this word all the time in your math future, is parallel. When you have lines that are parallel, there are two lines that never cross. What that means is they never intersect. That means that you can go on forever and ever in both directions on those lines, and those lines will never cross. So those are called parallel lines. And the symbol that we use is this. So what this is saying here, let's zoom in just real quick. What this is saying here is that QR, line QR, is parallel to line ST. Line QR is parallel to line ST. So our next vocabulary word is this one, which is perpendicular. So the word perpendicular refers to lines, or perpendicular lines. It refers to the angle that is created by those lines. So if you have two lines that are perpendicular, like we have here with line MN and PQ, the way we would talk about it, or the way we'd write it, is that line MN is perpendicular. Look at that upside down T. That kind of upside down T means perpendicular. These two lines, MN is perpendicular to PQ. What they mean is that it forms a perfect 90-degree angle. 90-degree angles are all over the place. Hopefully they're all over our homes, right? Because if our houses don't have walls that are 90-degree angles with the floor, then we are on unbalanced ground, or things are not as perfectly squared away as possible. And so I have floors that are not actually like that, but the goal is for them to be 90 degrees with the wall. And that 90 degree means that it's perpendicular. So the word perpendicular means forming a 90-degree angle. Lines in planes, we have another vocabulary word that is oblique. Lines in planes that are neither perpendicular nor parallel nor perpendicular, are called oblique. And so basically when we have lines that intersect and they're not perpendicular and they're not parallel, remember these two lines are intersecting at this point, we call these lines oblique. All right, so we got some vocabulary for ourselves. Let's see what else we can do. So a few more vocabulary phrases that we need to keep in mind. And this one is kind of a cool one, angle. We know what an angle is. We've seen them before. It's kind of like, I don't know, sometimes I think about it like an elbow, right? Like kind of your arm bending. When your arm bends, it forms an angle. And the angle that we just talked about was 90 degrees, but let's really look at the anatomy of an angle. When you have an angle, it has a corner that's called a vertex, right? That would be the elbow joint. And so the vertex is the point where the two rays that form the angle meet. And so the two rays are called the sides of the angle. So if we talk about the side, we could say side MD, like side ray MD is one side and side ray MB is one side. When we talk about an angle, this textbook doesn't do it, but we usually use a little symbol like that, and we name the angle with generally 3 letters. So this would be angle DMB, or we can have angle BMD, just as the text has down here. So what we would usually do is have a little symbol like that for angle. But here's the thing. You can't just use these 3 letters in any kind of order. These are the only 2 ways to refer to this angle that we have here. It is not appropriate to talk about this as, let's say, angle BMD. Oh, no, not BMD. I'm sorry. Angle BDM. That's not okay. And the reason why is because this middle letter must be the vertex. So if you're talking about angle BDM per se, you would be talking about this angle that I'm drawing here in pink. We will be talking about a whole nother angle indeed. Are you with me? So I want you to keep that in mind, that naming angles are important. We must be very clued into where the vertex or that elbow joint is. All right, so let me get this pink angle out of the way so we can talk a little bit more about angles. So we can sometimes what we also do, oh, there's the little angle symbol. Sometimes what we also do is we name an angle by just putting a number inside. And so I might say, okay, this is angle 1. Or sometimes we talk about an angle just by the vertex if there's no other confusion. So like you wouldn't do it if you had like another ray sticking out here and you only wanted to refer to this pink part. You can't call that A because you're not sure what A is. But as long as A is really clear that there's a little angle, there's only one angle or only 2 rays coming from A, you can definitely call this angle A, all right? Or angle A. And here, if you number the angle, if you put a number inside, you can call that angle 1. And so we have that here. The other piece of information is that angles all have names. So we're going to go over this again. I know we talked about it before, but I think it's worth talking about it again. When you have a right angle, it's a 90-degree angle. It measures 90 degrees. When you have an acute angle, I like to say little and acute. It's little and acute. It is going to be the measure of this angle, let's call it X. X has to be less than 90 degrees. It's going to be less than 90 degrees. So the measure of this angle, if this angle is called X, X would be 90 degrees. The measure of this angle, that would be less than. That's what that symbol is, less than 90 degrees. The measure of this angle has to be 180 degrees to form a straight angle. And the measure of this angle, an obtuse angle, obtuse is larger than 90. Let's say call that measure X. X would have to be greater than 90, right? 90 has to be less than X, or X is greater than 90, and it has to be less than 180, because if it's equal to 180, then it's a straight angle. So these are the angles that we're going to keep in mind, and we're going to talk about them in the next example. All right, so here in this example, it says which line is parallel to AB. And so if you're looking at it like I'm looking at it, you see AB is here. You know that CD is parallel to it. So we're going to write line CD, just like we know we're supposed to. Write the CD with lines, arrows at either end. So line CD, or we could have written DC because we have that. Which line is perpendicular to AB? So here's AB. We remember that perpendicular means that it forms a 90-degree angle. And so we're talking about this line BD here is perpendicular to AB. And so I'm going to write that line BD or line DB, right? I can name it the other way, but that line is perpendicular. And you can see that the textbook agrees. How many right angles are formed by 2 perpendicular lines? Can you see that? Can you Figure out how many right angles are formed by two perpendicular lines. All right, we can think about that together. If you have two lines that are perpendicular to one another, they don't just form one right angle. They don't just form one right angle. They actually form four right angles. So hopefully it's sensible when I say that this is a right angle and this is a right angle. This is also a right angle. This is also a right angle. So each of these angles will add up to 90, right? And if we added all four of those up, we'd get 360. If we just added up two, we'd get 180. And so we see how sometimes like skateboarders will say, oh, I did a whole 360. That means you went around all the way. You started in one place and you went all the way around. Or if you twirl or something like that, you can use that language of 360. All right. Here we have example 4, and we're going to talk a little bit about how we're going to label particular types of angles. So first thing they ask us about is the straight angle. So the straight angle, we remember, is an angle that forms 180 degrees. So the straight angle is this angle right here, angle AMD. Angle AMD. The next angle that they ask us about is an obtuse angle. And so when I look, see this is right, this is too small, but here's our obtuse angle. Our obtuse angle is here, and we can call it angle AMC rather, or CMA. So I'm going to call it angle CMA. CMA. All right. Two right angles. Okay, so for this one, we want two different answers. Let's see if we can do that. Two right angles. So one right angle is right here. That's one. And we do have another right angle right here. So we've got two right angles, and I will name them. One angle is angle AMB, and the other angle is angle DMB. Name two acute angles. So these are the ones that are less than 90 degrees, and they are little and acute. So this guy is less than 90 degrees for sure. And let's try another color over here. And this guy is less than 90 degrees also, because we see it takes two of these angles to make a 90-degree angle. So naming those two angles that we just showed were acute, we will call them angle, let's see, BMC and CMD. All right, so hopefully that's making good sense. So here in example 5, let's take a look at what we've got. It says that a power pole with two cross pieces can be represented by 3 segments. Name the vertical segment. Name a vertical segment. And so a segment from here to here is vertical. Vertical means, vertical segment means going up and down. I always get them confused, but vertical means going up and down because we think of our vertebrae and our spine, which goes up and down. So that's how I try to remember. So name a vertical segment, and that would definitely be segment AB, and we'd write it like that, or I could write it BA. Name a horizontal segment, and there are 2 horizontal segments. I always think about the horizon. The sun comes up over the horizon. No, maybe? Okay. So anyway, so that is what we're going to do. We're going to name one of these, and we can call it CD, or we could even call it EF. We've got 2 choices in terms of the horizontal segments. So either one are okay. And of course, we could name them in their opposite order, DC and FE. Name a segment perpendicular CD. We remember perpendicular means making a 90-degree angle. And so AB is the perpendicular segment. All right. All right, so later on, they're asking us to think about our walls and our floor as planes in our houses. And so it says that we may draw parallelograms to represent planes, something we talked about, and they're showing this sketch to reference the idea of a plane. Even though a plane has no boundaries, it goes on forever and ever, we can sometimes use walls and planes and walls and floors and ceilings to think about planes. I know this has been kind of long, but this is our final example before you can go ahead and do the practice set. And I just want you to just listen. I do think that it's been long, but I appreciate you sticking with me. This final example says to sketch two intersecting planes, which would best describe the location of the planes that you intersect. Sketching intersecting planes is really hard. And I for that reason, I left the textbook one here. But if you think about two planes that are intersecting, it will do something like this. I know we already have the picture, but I'm going to do this. And you're kind of thinking about this place as the intersection. This is what a picture would look like for me. And so these intersecting planes actually intersect because the planes extend forever and ever in either direction, they intersect in a point. Not really. A segment, almost it looks like a segment because we know the segment has endpoints. But remember, every time we talk about a plane, we say that it extends forever and ever in either direction. So the actual answer is a line because if the planes keep going, then the intersection keeps going and then we're going to have a line. Make sense? Hopefully it does. All right. I know this has been a super long video. You've got your practice set to do. Try to do the written practice. Go ahead and do every other one. You can do the odd ones. It's a little long, but 15 problems. I think you can handle it. Go ahead and do the good fight. And I look forward to talking to you soon about the next sections. Take care. Bye-bye. Here we are in lesson 8. We're going to talk about fractions and percents using an inch ruler. So we're going to think about that. What I want you to observe here is that couple vocabulary words. We want to keep our mind on denominator. That is the bottom portion of a fraction, and the numerator is the top portion of the fraction. And one concept that may have been told to you before or that you may or may not remember is that when we look at this thing here, I think it's actually called a vinculum or something like that. But when we look at the fraction bar, we really do think of it as a division bar. It really is saying divide. It's saying if I had one thing divided into 4 equal pieces, if I had one thing divided into 4 equal pieces. So I want you to keep that in mind. Now, here's what you're supposed to be seeing here. You're supposed to see that if you have 100%, which is the entire circle, and you divide it into 4 equal parts, each of those parts would be 25%. Each of those parts would be 25%. And that makes a certain kind of sense. 100 divided by 4 is 25. And so what this tells us is when I'm looking at this shaded region, which I know from my fraction practice to be 1/4, right? I'm also looking at something that can be called 25%. That's the take home. 1/4, the fraction 1/4 is equal to 25%. And we can look at fractions in that way. So let's take a look at this idea of looking at fractions and mixed numbers as well. So sometimes we can have a mixed number, and a mixed number is when we have a fraction whole number combo. So this is a great example of a mixed number. When you have a mixed number, you are looking at a whole, however many holes, in this case 2 holes, and then the fraction part, 3/4. So you've got 2 holes and 3/4 in this mixed number. Because we already talked about the circle being 100% or all of it, right, when we're considering a whole. So this is 100%, this is 100%. Remember each of these, we broke them down, they were 25% each, right? So if that's the case, this looks like this fraction 2 3/4, so this mixed number 2 3/4 written out is actually referring to 100, 200, 275%. This could be considered 275%. So now the question is, how do you think we would write 3 and 1/4 as a percent. So remember, we'd have 3 wholes, and then 1/4. That one didn't make it to circle hood, but that's okay. So we'd be looking at this situation that I'm shading in. So 100, 100, 125, 325% is what we'd be looking at. Let's take a moment to look at the first example. So this first example is asking us to name the shaded part of the circle as a fraction and as a percent. The first thing we want to do is deal with our fraction idea. You notice that these are 5 parts. So our fractions denominator describes how many parts we're dealing with, and so that's going to be 5. The parts that we're concerned about are the shaded ones, and there's 2. So 2/5 or 2 out of 5 is what we're looking at. The next thing we want to think about is how we're going to think about it as a percentage. Well, the whole thing is 100. And if we take 100 and we divide it by the parts, which is 5, we see that each of those parts represents 20%. So if we had 100, we consider that 100, divided it by 5, we'd get 20%. This means that each of these segments or sections or slices of pie, because I'm hungry, each of these refers to 20%. If we have 20% for each of these, then we know that the shaded region is 40%. And that's what our text tells us. Example 2 is going to ask us the following. Which of the following could describe the parts that is shaded in the rectangle correctly? So I didn't read that well at all, but that's basically what they're talking about. All right, so when I look at this, I can see the shaded region is more than the halfway point. And so that is significant for me. I always want to think about what's going on. So the shaded region is definitely half, so I know it's over 50%, right? Know that it's more than 50%, and I know that it's more than 1/2. So that already lets me know that 1/2 can't be the answer. 40 can't be the answer because that's under 50%. And since this is a little bit over 50%, 60% is my guess. In example 3, we're switching gears and we're looking at a number line. And so we're being asked, okay, so if you have this point A, what is the mixed number that is represented by this number line? So we already know we've traveled past 8 whole spaces. So I know part of A is going to be 8. It's going to be 8 and something. 8 in what though? I look at the number of spaces from 8 to 9. 1, 2, 3, 4, 5. I see that each whole is broken down into 5 equivalent parts. And so I can see that A is placed 2 of those spaces past 8. So that would be 8 and 2/5 would be the mixed number that is represented by point A. So here in example 4, we're going to do a little bit of measuring. It says use an inch ruler to find the length of AB, BC, and AC to the nearest 16th of an inch. So I copied, let's see if I can grab it. I copied this inch ruler and I hope that it's kind of okay. Let's see. So if we're going to measure this, let's do AB first. We're going to start right there at AB. They said 16th of an inch because we need to use something that's broken down into 16ths, and we happen to have that here. So there's 16 little bits in here. So now I know that from here to here is not quite 1 inch. It's going to be, if I'm thinking about the 16s, it's going to be 14 16ths, right? Let's count together. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. So I can write my fraction as 14 16ths. But you might be looking at that and seeing that you can actually reduce that fraction. If you notice, if we thought about this in terms of eighths, which I'm making these lines darker, it would be 7/8. And that makes sense because if I divide the top and bottom by 2, I get 7/8. So AB is 7/8. And they have the solution here that they're doing, but we're just going to talk about it ourselves. So AB is 7/8. BC, we would take our ruler and do the same thing again. Let me carefully take our ruler. Come on, ruler. And we're going to move it over here. And let's see if we get the same thing that the text gets. So I'm going to erase some of this stuff here. And we are going to see that BC is 1 inch and some more. It looks like we've got 1 inch and 1, 2, 3, 4, 5. That's 10 sixteenths or 5/8. So we end up with 1 5/8 for the length of BC. If we wanted to find AC, we could add AB and BC to get the answer. So the length of AC is equal to AB plus BC. We already know that AB is 7/8 and BC is 1 5/8. So if I'm adding these two fractions together, with mixed number and fraction, I'm going to get 1 12/8. Remember, I can add these fractions together because they have a common denominator, but the numerators, I need to add those together. But this is an improper fraction. I'm going to divide that 8 into 12. It goes in there one time. And then I have 1. And then that's 1 from here. And then from this fraction, 12/8, I have 1 4/8. So 1 from the beginning plus 1 4/8, well, that's 2 4/8. And if I want to be a nerd, which I do, I'm going to change this 4/8 to 1/2. So 2.5 is the length of AC. And I think the textbook is going to bear us out somewhere there if that's what they asked us about. But I don't see them giving it. Oh, there it is. It's here. 2.5 is that length. All right. So with that in mind, we're going to take a look at arranging fractions in order, which is something that we should know how to do. And probably one of the best way to do this is to, what they want us to do is to use this ruler to do it, which is fine. So if we were looking, I'm going to just label this in red so we can see a differentiation. So 1/2 is here. 1/4 is here. 5/8, so these are eighths. 1, 2, 3, 4, 5. 5/8 is here. Put a little arrow there. 7/16. 1, 2, 3, 4, 5, 6, 7. All right, that's right there. Let me make that a little bit narrower. Let me do it again. 1, 2, 3, 4, 5, 6, 7. That's right here. So that's 7/16. So now that I see it laid out on a ruler, I can easily determine that 1/4 is the smallest. 7/16 is the next smallest. 1/2 and then 5/8 to finish out the list from least to greatest. Now you are free to go ahead and do the practice set for this section. Make sure it makes sense. Let me know if you have any questions, and I look forward to talking to you soon. Take care, sweetie. Bye-bye. Here we are at lesson 9. We're going to be talking about adding, subtracting, and multiplying fractions, and we'll also talk about this concept of reciprocals. As we discussed before, whenever we're adding fractions, we can do it as long as we have a common denominator. And so when we add fractions, I want you to remember that the denominator tells me how many pieces we've broken the fraction up into. So look at this and just realize I have 1/7, and then I've got 2/7, and then I have 3/7. Basically, I'm talking about the same thing. And since I'm talking about the same thing, the denominator is common, I can literally just add the numerators. And in this case, 1 plus 2 plus 3 is 6. My denominator stays the same because I'm still talking about sevens, and the answer is 6/7. Here, I'm dealing with a fraction of sorts. If you think about it, this is 33 1/3 and 33 1/3. They're mixed numbers. I'm adding them together. What I'm going to do is add the fractions together, and then I'm going to go ahead and add the whole numbers together. So when I add the fractions together, 1/3 plus 1/3 is 2/3. Denominator stays the same, just add the numerator. And then 33 plus 33 is 66. So when I add these two percentages together, I get 66 and 2/3%. Example 2 is asking us how much money is 1/4 of a dollar plus 3/4 of a dollar. And so we know that 1/4 plus 3/4 is going to give us 4/4, which is 1/2. So in this case, the answer is 1 whole dollar. So remember, when we're subtracting, we also need to make sure we're talking about the same stuff. The denominators need to be the same. And so in this case, I'm subtracting 3 and 5/9. Well, I'm subtracting from 3 and 5/9, 1 and 1/9. And when I do that, I'm going to look at the fractions and see if I can subtract them. 5/9 is quite enough for me to take 1/9 away, and I'm left with 4/9, so that's cool. And then I'm going to deal with the whole numbers next. 3 minus 1 is 2. So the answer here is 2 and 4/9. Let's take a look at this one. 3/5 minus 3/5. Well, if I have 3/5 and I'm taking 3/5 away, I'm left with 0/5, or in other words, 0. So that's how we would handle example 3. So here in this part of the lesson, we're thinking about why multiplying fractions works. You may have heard it before. When you multiply 1/2 times 1/2, you're just going to multiply straight across. You don't even have to worry about common denominators, even though we have it here. And the question is why? Why do I take 1/2 and multiply by 1/2 and I get 1/4? Well, if I take 1/2 and then I take 1/2 of that, I am left with 1/4. So when I multiply fractions, I end up with kind of a littler or smaller amount. That often can be the case. All right, so what I'd like us to do is to try some of these problems here in example 4. So it says find each product. So 1/2 of 1/3. The cool thing about multiplying fraction is you do not need a common denominator. We're just going to multiply straight across. 1 times 1 is 1, and 2 times 3 is 6. And that's what we get over here, 1/6. Even if we're doing many numbers, we can multiply those together. 1/2 times 3/4 times 1/5. No need for a common denominator here. So if I multiply straight across the top, right, my new numerator is simply going to be 3 because 1 times 3 times 1 is 3. My denominator, on the other hand, is going to require me to multiply a few more things. But we got this. When I multiply 2 times 4, I get 8. When I multiply 8 times 5, I get 40. I could have even done that in a different direction or a different order because of our commutative property and our associative property. I could have multiplied 5 times 2, which is 10, and then multiplied by 4 and got 40. But anyhow you shake it, the answer is 3/40. One important property that we need to know is that fractions, all numbers really, have something that we call a reciprocal. And I'm going to scooch up here and look at it. So a reciprocal is what we get when we invert a fraction. So I'll show you a couple of examples of fractions and their inverses. So if I have, let's say, 4/7/9 and 8/21. Let's say those are my fractions. I can write them as I can write their reciprocal, and I'm going to write their reciprocal in red. So the reciprocal of 4 is 1/4, because we always know when we have a whole number, we can write it as a fraction by putting a 1 underneath it. So the reciprocal could be 1/4 there, would be 1/4. The reciprocal of 7/9 is 9/7. And the reciprocal of 8/21 is 21/8. So we're really just inverting it or flipping it to get the reciprocal. The thing about the reciprocal is if you take these two numbers and you multiply them together, the product of a number and its reciprocal is always 1. So let's think about that. If I were to multiply 4/1 times 1/4, I'd get 4/4, which is 1. The same thing would happen for each of these. 7 times 9 is 63. 9 times 7 is 63. That's 1. The product of a number and its reciprocal is always 1. Similarly here, if I were to multiply these guys together, I would get 168 over 168, which is still just 1. So when we talk about the reciprocal, it's flipping the numbers of a fraction or the fractional version of the number. And when you multiply it, you're always going to get 1. So here is a property of math that we want to keep in mind, inverse property of multiplication. If you want to get the number 1, you multiply by the reciprocal or the inverse of that number. All right? Okay, let's go ahead and see how that plays out for this example 5 that I'm doing at the bottom. I won't show you the whole thing so we can do it without looking at the answers. Find the reciprocal of each number below, then multiply the number with the reciprocal. Cool, we've done this. So if I start off with 3 over 5, then I'm going to write the reciprocal in red as 5 over 3. When I multiply those two numbers together, I'm going to get 15 over 15, which I now have space to write as 1. Let's try the same thing with this one. Here we have the number 3. I can write 3 as 3 over 1. When I take the reciprocal of that, I get 1/3. If I multiply those two values together, I end up with 3 over 3, which is 1. So here in example 6, we're going to be looking at how can we figure out what this n value is. So I have 3/4 times some number n, right? Some number n. Let me actually make a little box for it. Some number n is going to give me 1. But we've just been working and we realize that every time we multiply a number by its reciprocal, we're going to get 1. So that helps me figure out what n is very quickly. N has to be 4/3 because I know that anytime I multiply a fraction by its reciprocal, that's what's going to give me 1. And I think that's what they have underneath all of this stuff. So yeah, so we get 1 when we multiply 3/4. 3 times 4, we get 12 over 12, which is 1. Let's take a look at this. How many 3/4 are in the number 1? Well, since we know that 3/4 times 4/3 is equal to 1, that lets us know that there are 4/3, 3/4 in the number 1. I know that sounds crazy, but if you think about your multiplication, you'll see that it bears out. It makes sense. All right, so I'm going to do a quick little example. If I say 5 times 2 is 10, and then I said, well, how many 5s are in 10? You know that the answer is 2. Same thing here. 3/4 times 4/3 is 1. How many 3/4 are in 1? The answer has to be 4/3. You are ready to do your practice set. Make sure you get that done and then do the next section where we get to do some written practice and review. Make sure you do odd ones there. All right, talk to you soon, sweetie. Bye-bye. We are in lesson 10. We're going to be writing division answers as mixed numbers and improper fractions. So let's go ahead and take a look at what our new concepts are. So here, we remember how to do division such that we get a remainder. Totally makes sense. But if you think about it, we can actually look at this remainder as a part of the 4 or as one of the fourths that we're trying to cut it into. I want you to imagine that you have 8 luscious cupcakes that you are going to share. You must share. You have to share them with your 2 siblings, just 2 of your siblings. All right. For some reason, you got to share them with your 2 siblings. So you decide that you're going to share it. So that's 3 of you. You're going to share these 8 cupcakes. And you know, if you do that, 3 goes into 8 rather. 2 whole times, 2 times 3 gives us 6. And then we have a remainder of 2. Now, these are good cupcakes. They're good cupcakes. Are you really going to let 2 cupcakes remain? I mean, you gobble up 2 and your sister gobble ups 2 and then your brother gobble ups 2 and then you got 2 left over. You can't take them to any other siblings. You can't bring them home to your parents. Can't give them back. You guys got to do something. Do you just throw them out? No. You're not going to leave them as remainders. You are going to break those cupcakes up into wonderful, equivalent 3 pieces themselves, right? Think about it. You know you will. You know you will. You're going to break it up into 3 equal pieces. So each of you you're going to break them up into thirds, right? So each of you will get to enjoy what's left over. So in a way, right, you guys won't just get 2 each. You guys will probably, to be fair, you'll get 2, and then you'll get 2/3 of this one, and then your brother will get 2/3 here, and then your sister will get 2/3 here. So technically, when you divide 3 or 8 by 3, you get 2 and 2/3. Let's look at where that 2/3 is coming from. You get 2/3. So what we're going to do now, instead of just writing this as a remainder, right? 8 divided by 3 is going to give us 2 with a remainder of 2. We're going to take that remainder 2, right? Let's go back through the math. Take the remainder 2 and put it on top of the divisor. So the answer is 2 and 2/3, because this is completely dividing the whole thing down and writing our remainder really at what it is as a fraction, as a fractional part of what we have. So that's what our text is talking about here. That's what they're showing us, that when we get a remainder of 1, instead of just leaving out there and say it's a remainder, we're going to show that that's really 1/4 of a whole if we completely divide that 25 up. All right, let's look at this first example. So remember, we're looking at percentages. It says what percent of the circle is shaded? Well, we remember that 100% is the whole thing, and we can see that this 100% is being split into 3 equivalent parts. And so we're going to write that as 100% divided by 3. And if I rock some long division, 3 goes into 100. Let's check it out. 3 goes into 10. 3 can't go into 1, but it can go into 10. So 3 goes into 10 3 times. 3 times 3 is 9. I'm going to get 1, drop my 0. 3 goes into 10 3 times. 3 times 3 is 9. Subtract, I have 1 as a remainder. But we don't write 1 as a remainder, right? Remember, we're going to take that remainder and put it right over our divisor. So we get 1/3. So the answer here is when I divide 100% by 3, I get 33⅓%. And that's my answer, 33⅓%. All right? So this example is a pretty good one of thinking about how do you draw and shade circles to illustrate that 5/3 is really 1 and 2/3. So we need 5/3. And so what we would do is we would draw 2 circles. Let's not use the white. We would draw 2 circles, and those 2 circles would give us an opportunity to talk about 5/3, because in one circle, we only have 1/3, or we only have 3/3. So if I make my thirds here, that's only representing 3/3. So I need to do another circle. Let's see if that kind of works out. And then I need to make another 3/3. I'm trying to make these look like thirds. Okay, so I've got that. So now I can see that I can highlight this as 1/3, 2/3, 3/3. Let's do it this way. 3/3. And then 4/3 and 5/3. So this represents 5/3, and we can see that that's 1 and 2/3. So drawing the circles were helpful, even though my circles were not as pretty as the textbooks. Just wanted us to do it together. In example 3 here, we're going to see that we can practice the idea of changing improper fractions into mixed numbers without having to draw the picture. So one thing we can do is figure out how many wholes are in here. 5/3 has 1 whole, that's 3/3, with 2/3 remaining. So that shows that we have 1 and 2/3 as we got here. Similarly, 6/3 can be 3/3 and then another 3/3. So that shows 1 and a 1, which is 2. So that's another way of considering changing our improper fractions into mixed numbers. In this example, we see that we have not only a mixed number, but a mixed improper fraction. So let's take a look at the improper fraction portion. So we see we've got 3. 7 over 5 can be written as 5 over 5, and then 2 over 5. So we broke down the fact that this is a whole number 1. So now we're really looking at 3 plus 1 plus 2/5. And as the text got it, that's really just going to be 4 and 2/5. In example 5, we're just called to do some things that we've been doing before, some addition, which is going to get us 8/5, but that's an improper fraction. So we break it down as 5 over 5 plus 3/5, which is really just 1 whole and 3/5. Here we're asked to multiply. We know when we multiply fractions, we multiply straight across. So we get 15 over 8. That 15 over 8 is an improper fraction. So we can look at it as how many times does 8 go into 15? It does 1 whole time, and then it has a remainder of 7. So we get 1 and 7/8. We could also have written it as 8 over 8 plus 7 over 8 to show that 1 whole in that fraction. And then over here, we're going to be adding this stuff together. Let's go ahead and add our whole numbers, which gives us 2. And then we'll add our fractions, which gives us 6/5. And we'll change this improper part to a mixed number. So we get 2 plus 1 and 1/5. That's what 6/5 breaks down into. Now that we have that, we realize that this is just 3 and 1/5. Again, as the text shows us. To write each of these mixed numbers as an improper fraction, we could do it in the way that the text shows us. It says, hey, you've got 3 as a whole, then write 3 as a whole number, 3 over 3, and 3 over 3, and 3 over 3, then 1/3, then add them all up. That's totally fine. You might also realize that, honestly, you're just multiplying 3 times 3, and you get 9/3. So multiply the whole number times the denominator, then add the numerator. So 3 times 3 is 9, plus 1 more is 10. And then you're going to keep the denominator the same. Let's try that technique again. 4 times 2 is 8, plus 3 more is 11. The denominator stays the same, so we're dealing with 11/4. Finally, 12 times 2 is 24. Add 1 more, and we get 25. 25/2 is that final answer. So this is the end, and they're showing that method down here. This is the end of our lessons for right now. I want you to take a look at the practice. Make sure you do those. Do the written practice. Every other one is fine. Let me know if you have any questions, dear. I look forward to talking to you soon. Bye-bye.